Okay, so this is the second part of 7.2, and we're talking about washer method. All right, and again, we're dealing with volumes of rotation. Now, what we did in the first part was we basically just dealt with one curve like this, and we would rotate it around the x-axis between 2 points. So we were rotating this volume around this curve, and then when we took a slice through there and took a look at the cross section, it looked like a solid disc. And this is the disc method. Okay, this one, what we're doing is slightly different. We're going to be rotating an area bounded by two curves. About some kind of x-axis, something like this. And it's going to give us the washer method. Because you're going to have something which is going to look like this. There's one curve, there's another curve, and here's the solid, and for rotating it about the x-axis. Then we have, and if we take a slice through this, what you'll notice is that this part of it gives me my solid, which is the volume. This part here is a hole. And then if we rotated this guy back around, if we continue to rotate it, it would look like this. And so I would have hole and then solid. And so if we take this slice and then look at it in cross section, again I'm going to have a circular shaped object with this point being here and this point being here. However, you'll notice that from here to here, I've got a hole. So this is solid, and this is my hole in here. So the actual volume is just going to be around in here. And the thinking is very similar to what we did on the last one, where basically, I'm going to go back. What we're going to do on this is take this solid, but if I calculate the volume for this guy, so if I integrate pi in the integral from whatever my bounds are, a to b, and this would be the intersection points of these two, of this guy right here actually is y is the square root of x, and this guy right here is y is x squared. So if I do this guy right here, so it's going to be the square root of x squared, which is my r dx. So that would give me the solid for everything between these two right here. But I've got a hole in the middle of it, so I have to subtract that. And that's going to be my integral from a to b of x squared dx. Okay, So the first thing we need to do then, let's deal with this problem. The two functions we're dealing with are going to be y equals the square root of x and y equals x squared. And we've got the graph. And so first thing we need to do then is figure out where these guys intersect at. So we set them equal to each other. So I'm going to have the square root of x equals x squared. Get rid of the square root, I'm going to square both sides. That gets me x equals x to the fourth, or x to the fourth minus x equals 0, or x times x cubed minus 1 equals 0, which means my first point of intersection would be where x equals 0. Then I'm going to have x cubed minus 1 equals 0, x cubed equals 1, which means x is 1. So these are my 2 points. That's A and that is B. And now we're going to go back in and we're actually ready to take care of these things. Now what I notice is when I do this, the way these integrals are going to look is going to be pi times your integral from A to B of your r of your outer one squared minus the square of your inner curve. This is what gives you your solid minus the whole. Okay, so we're ready to go on this. So I know from looking at my graph that my outer one was the square root of x. My inner was x squared. A was 0, B is 1. So now I'm ready to come in and do my integral. So it's going to be pi times the integral from 0 to 1 of x to the 1/2 minus x squared dx. And now we just got a simple little rewalk problem. So I add 1, this is going to give me pi times, I'm going to have 3/2 x to the, 2/3 x to the 3/2 evaluated from 0 to 1 minus x cubed over 3 again evaluated from 0 to 1. So now we come in and we do our arithmetic. So we're going to have pi times then 2/3 of 1 to the 3/2 is going to be 1 minus 0 minus, and I'm going to have 1/3 of 1 cubed is 1, 1 minus 0, which is going to leave me with pi times 2/3 minus 1/3, which is going to leave me with an area of pi over 3. 2/3 minus 1/3 is 1/3. And so this is how you do this guy right here. Okay. So the steps on these are basically following. Step 1 is going to be to graph it and then identify your outer and enter. Same idea is going to hold true for y if you integrate with respect to y. Then step 2 is going to be find points of intersection. And then step 3 will be to integrate. Actually, what I do is set up the integral of outer minus inner and simplify. Then you integrate. Evaluate at the endpoints. And step 6 is slap the pile on the end. And you're done. Okay. I'm going to work another one which is a little bit more complicated. This one you're going to rotate about the x-axis. And the functions you're given are y equals x squared plus 1, y equals negative x squared plus 2x plus 5, x equals 0, x equals 3. So the first thing I'm going to do then is come in and graph these things. So the first one I have is x squared plus 1. Second one I have is a negative x squared plus 2x plus 5. And then I'm going to have x equals 0. Whoop. And finally I'm going to have x equals 3. And I'm going to want to zoom out on this thing. So let's take a look at these two first. And as you can see, the solid we're dealing with is right here. Anyway, it's within this area right here is my solid. Okay? And we're bounded at 0 and at 3. Okay, so now we've got some idea of what we're dealing with here. We've got to find our area of intersection on these guys, points of intersection. So we set them equal to each other. So I've got x squared plus 1 equals negative x squared plus 2x plus 5. I'm going to move these over. I end up with 2x squared minus 2x minus 4 equals 0. Divide everything by 2. That gives me x squared minus x minus 2 equals 0. I can factor that. I get x minus 2, x plus 1, or x equals 2 and x equals negative 1. So I know my bounds are negative 1 and 2. However, you notice we're cutting this off at 0. So that's going to be my A. We also are going over to 3. So this is going to be my B. So let's go back in and take a look at what's going to happen with this thing and relook at our graph. So we're going to start here. All right, and you notice when we look at this that the negative x squared, which is this one, is on top. Except once we get over here to 2, and between 2 and 3, they switch over. So we're doing this area, but we're also doing this area right in here too, if you look at it. All right? This area right in here. Okay, so now that we've got that, then we're going to set up our integrals. So my A is going to be 0. My B is going to be 3. However, I'm going to have two sets of integrals. I'm going to have a set of integral from 0 to 2, which is where my negative x squared plus 2x plus 5 is on top. And that's going to be squared minus the x squared plus 1 squared dx. So that's from 0 to 2. That's where this one was on top. And then I'm also going to have to add a second integral, which is going to be from 2 to 3. And that's where we switch. The x squared plus 1 squared is on top. And that would be minus the x squared plus 2x plus 5, negative x squared, 2x plus 5 squared is on bottom. So let's do this one first. And the pain on this is squaring this term. You've got a negative x plus 2x squared plus 2x plus 5. And then you're squaring it, so you multiply it by itself. And so when you do that, I end up with an x to the 4th minus 2x cubed minus 5x squared. Then I have to distribute this 2 in, so that's going to give me a minus 2x cubed. And then that times that will give me plus 4x squared. And then plus 10x. And then finally I take my 5, that will give me minus 5x squared plus 10x plus 25. I group all my like terms, I lump them all together, and I'm going to end up with an x to the 4th minus 2x minus 4. So I've got an x to the 4th minus 4 x cubed minus 6x squared plus 20x plus 25. And we're going to want to keep that, that's our square. And then we have to expand the other term, which is the x squared plus 1. So remember, this was my negative x squared plus 2x plus 5 squared is this thing. And then the x squared plus 1 squared is going to give me x to the 4th plus 2x squared plus 1. And then we subtract these two. So I'm going to have x to the 4th minus 4x cubed minus 6x squared plus 20x plus 25 minus x to the 4th minus 2x squared minus 1. The x to the 4ths drop out. And I'm left with now my integral from 0 to 2, which is a negative 4x cubed minus 8x squared plus 20x plus 24 dx. And then I do this, I'm going to be left with the negative x to the 4th, evaluated from 0 to 2, minus 8 thirds x cubed, evaluated from 0 to 2, plus 10x squared, evaluated from 0 to 2, plus 24x, evaluated from 0 to 2. And when I plug all of these things in, I don't want to do all of this. You should end up in the final product with a 152 pi over 3. Now remember, that's just the first integral. That's the part from 0 to 2. So now I have to add in the part from 0 to 3, which is what we do is we switch these things. So I'm going to have my x squared plus 1 squared minus the negative x squared plus 2x plus 5 squared dx. And I plug everything in. I've already done these, so I'm going to have x to the 4th plus 2x squared plus 1 minus, I got an x to the 4th. And I already expanded these out, which is why I told you to write them down to begin with, and that's always a really good idea. I have a plus x to the 4th plus 4x cubed, a minus and a minus, plus 6x squared minus 20x minus 25. And then I'm going to integrate all these things. These things are going to go away. I'm going to combine my like terms, so I'm going to end up with an 8x squared, combining this and this. Then I'm going to have plus 4x cubed, and then 1 minus 25 minus 24. Minus 20x. You always forget the term. And this is what I'm going to integrate from 2 to 3. And when you do this, you're going to end up with an 8 thirds x to the cubed evaluated from 2 to 3 plus x to the 4th evaluated from 2 to 3 minus 24x evaluated from 2 to 3 minus 20 minus 10x evaluated from 2 to 3, and when you plug everything in, that ended up equaling to 125 pi over 3. Remember, I have a pi out on the end of it. And then we add the two together, this 125 pi over 3, plus the 122 pi over 3 we got from the other one. You ended up with 277 pi over 3 is your volume. And this is how you're going to do these things. It's very similar to the other thing, except you're going to have to subtract the inner thing we've got here, because this is what makes a hole. This is what makes it a washer rather than a disc. We have a hole in the middle of it. So you're going to have to do the outer one squared minus the inner one squared.